In this video, we're going to find prime numbers p and q such that p cubed minus q to the power 5 equals p plus q all squared. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. I've tried several small value cases, but I only got one pair of solution, which is p equals to 7 while q equals to 3. I wasn't sure whether this is the only solution, but I had a feeling that this might be the case. So I proceeded by considering mod 3, aiming to show that this prime q must be congruent to 0 mod 3, and by the fact that it's a prime, the only option left would be q equals 3. So I went on by considering mod 3. So in general, both p cubed and q to the power 5 can take any possible value mod 3, either 0, 1, or 2. Now let's take a look at that case by case. Say when p cubed is congruent to 0 mod 3, now that means p itself is a multiple of 3, and since it's a prime, that means p has to be equal to 3. But notice that the right side is a perfect square, which means it's non-negative. So that means p cubed must be at least q to the power 5, and we know that there's strictly larger than q to the power 3 because q is a positive integer that is at least 2, and so we have p to be larger than q. But now we're restricted to p equals to 3. So q must be a prime number that's even smaller than 3, and the only option for q now is that q equals 2. But then p cubed minus q to the power 5 is still negative. 3 cubed minus 2 to the power 5 is still less than 0. So no solution for this case. Now we move on to the other cases. If p cubed is congruent to 1 mod 3, then of course p is congruent to 1 mod 3, and we can put it into the original equation under mod 3. When q is congruent to 0 mod 3, we're just testing case by case. 1 minus 0 has to be congruent to 1 plus 0 all squared mod 3, so it's true. So we can keep this case for the time being. When q is congruent to 1 mod 3, 1 minus 1 to the power 5, which is just 1, is congruent to 1 plus 1 all squared mod 3. But this cannot happen because the left is 0 and the right is 4. Whereas for q is congruent to 2 mod 3, 1 minus 2 to the power 5 has to be congruent to 1 plus 2 all squared. And that's not true again because 1 minus 2 to the power 5 is minus 31, which is not a multiple of 3, but for the right side is congruent to 0 mod 3. So we've again removed two cases among p equal congruent to 1 mod 3. Next, we can take a look at p cubed congruent to 2 mod 3, which means p is congruent to 2 mod 3. Then 2 minus q to the power 5 is congruent to 2 plus q all squared. We can do similar things. Again, for 0 mod 3, not true. Then 2 minus 1 is congruent to 2 plus 1 all squared mod 3. Again, not true. We can foresee that similar things would happen when q is congruent to 2 mod 3. This time for the left is minus 30 multiple of 3, but for the right it's not. It's 4 squared, which is 16. So that means after looking at all the cases one by one, the only case that would work, it will possibly work, is this one. Under the case that p is congruent to 1 mod 3 and q is congruent to 0 mod 3. So from this we know that p can't be 3 instead, but q has to be equal to 3. So therefore p cubed minus 3 to the power 5, which is 243, is equal to p plus 3 all squared. So we turn to solve for cubic. Now we can test that one by one. The smallest prime that is congruent to 1 mod 3 is 7. So let's see if p equals 7 works. And miraculously, it really works. And from p squared plus 6p plus 36 equals 0, there are no other real solutions. So p must be equal to 7. So that means p equal to 7, q equals to 3 is the only solution to this problem. Of course, we can do some checking. And we find out that both sides will be equal to 100. So that means 7 and 3 is a pair of valid solution. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.